We're going to be talking about the mean. So that is the expected number of successes in a binomial distribution. The standard deviation, so that we can create intervals and we can kind of analyze the data a little bit better. And then we're also going to be doing what we call a quota problem. So sometimes in the world of statistics, we don't necessarily know the probability that we're going to end up at, but we know what we want it to be. So something could happen. We don't know the probability of that thing happening. But as a business, I may say that I want to be 98% sure that only 2 people will succeed in this game show. Or I want to be 99% sure that if we do this raffle, that we're going to have at most 3 winners. So you want to have a certain level of confidence. You know how many successes you want, but then you're going to turn around and say, all right, so how many people can we let play this game, given that I only want 3 people to win at the most? So can you offer it to 10 people? Can you offer it to 100 people, 1,000 people? It's that number that we're trying to figure out with the quota problems. So that's going to be using Google Sheets and a little bit of guessing and checking. By a little bit, I mean it's entirely guessing and checking. You're just typing in a number and then seeing if it gets to the percentage you want. But that'll be the last problem we get to. So the part that you're not going to be responsible for is the book brought back bringing the binomial distribution to being a bar graph to a histogram. And in the homework, they ask you to create histograms. You'll notice in the homework, I did not include part A for most of the problems. That's the one where you're creating a histogram. So don't create a histogram. You don't have to go through that headache of doing that. So these first few slides aren't really important because it was just a refresher of how to create a histogram. All right, this first question is important because your first question is going to ask you to look at 4 different distributions. Yes, and you have to select which distribution would relate to which situation with its probability of success. So what I'm going to do in the sheets is just show you what our distribution would look like numerically, and then talk about what it would look like graphically and how we could kind of make a future assumption about other distributions. So we have Jim here. He enjoys playing ball, and he figures that he makes about 50% of his field goals that he attempts during a game. Make a table and a histogram showing the probability that Jim will make 0, 1, 2, 3, 4, 5, or 6 shots out of 6 attempted shots. This is the point when people usually say, why did you write field goals? That is what a basket is called in basketball. It's a field goal. So if you look up stats, it'll be like FG percentage because it's a field goal percentage. That's what they shoot. In a 3-point field goal percentage, 3-point FG. Anyway, so I'm going to go ahead and calculate the probabilities for each of these 7 outcomes. So 0, 1, 2, 3, 4, 5, and 6. So here we are. We have Jim making 0 out of 6 shots. Now, if I am going to make 50% of my shots, I probably don't expect to miss every single one of them. I also don't expect to make every single one of them. What we're going to find is that as we do these probabilities, it is going to get to a peak probability. That is the greatest chance of success. And then as we move away from that greatest chance of success, it will become less likely to get those values. So in theory, this may be our lowest probability. And you might be thinking to yourself, well, you're probably expecting to get 3 out of the 6 because that's 50%. And you are correct. So I'm going to go ahead and type in the binomial distribution. Since I want exactly 0, then I'm going to be doing false. And so there's only a 1.6% chance of missing all the shots. Speed this up. So the next one's going to be for 1. Let's see if I can cheat. Nope, but that's all right. They're all there, so now I can just change them. Sometimes Google Sheets will recognize a pattern and will do it for you. They thought I wanted every other. The jerk. All right, so when I look at these probabilities, I'm noticing that starting at about 1.6%, then it goes up to 9%, then 23, then 31, then back down to 23, then 9, then 1.6%. So this is going to be completely symmetrical. Now, if we wanted to use our imagination and think about what that histogram would look like, that would mean that at the middle of our histogram is going to be the highest bar, and then as we move away from that, the bars are going to be decreasing in a symmetrical fashion. So a distribution that would be a 50%, right in the middle is going to have the highest probability of success. Now that highest probability is only 31%. You may have expected it to be higher, but remember, we have to add all 7 probabilities and they have to equal 100%. So it doesn't quite mathematically make sense that you would have something crazy like an 80% chance of success at your most common number of successes, because you still have, in this case, 6 other probabilities that you'd have to add together. If I had something like 80% chance of success, now all of a sudden, if there's an 80% chance of success, what you're going to find is that 4 and 5 are going to have the higher probabilities. And as you work your way towards 0, it's going to steadily decrease. So that would be more of a skewed left sort of situation, because as you're going to the left, it's decreasing. If you only had, let's say, a 10% chance of success, then that means that the 0, the 1, and the 2 are going to have the highest probability. And as you move to the right, it's going to be skewed right. It's going to be decreasing, because you're expecting, if you only make 1% of your shots, 10% of your shots, that you're going to either make 0 or 1 of those 6 shots. So the probability would be on the left, and it would decrease as you go to the right. So your first homework problem is going to be looking at 5 graphs, 5 histograms with, 4, I can count, 4 histograms with 4 associated probabilities, and you just have to say which graph goes with which probability. So if it's at 50%, it's the highest in the middle. If it's a low percent, it's the highest on the left. If it's a high percent, it's the highest on the right, and anything kind of in between. All right, so how we can find the expected number of successes for any binomial distribution. So the last one was easy. It's a 50% chance. So intuitively, you thought, well, half of 6 is 3, so you should be making 3 out of 6. Well, intuitively, you just thought a formula for the mean of the binomial distribution. The official formula is n times p, which you take your sample size and multiply it by the probability of success. So if you're trying something 10 times and there's an 80% chance of success, 80% of 10 is 8. So 8 would be the expected number. So that formula is pretty easy because it's pretty intuitive. The standard deviation, not so much. The standard deviation is the square root of the sample size times p times q. Now, p is your probability of success, and as a reminder, q is the probability of failure. So they will give you one of those probabilities, and you have to subtract it from 100% to find the other one. And then if you ever forget, I just went through and explained that. So just to finish off the problem that we had started, if I wanted to know the mean, which is the expected number of successes, I am going to do n times p, n being 6, p being 0.5. So I get that the expected number, or the average, would be 3 out of 6. And the standard deviation is going to be the square root, which is SQRT, of 6 times 0.5 times, not 0.5, yeah, times 0.5. So the 6 was the sample size, 0.5 was the probability of success. The second 0.5 was the probability of failure. 50-50 shot, half the time they make it, half the time they do not. So in this problem, the mean is 3 with a standard deviation with a give or take of about 1.2. Almost there. Last one is the quota. So how many shots should Jim take if he wants to be 90% sure that he will make at least 4 shots? So if we want to be 90% sure, we know the probability. So Jim's going out on the floor and we're like, all right, we need to make these 4 shots. How many shots does Jim need to take in order to be 90% sure that at least 4 of them will go in? So this team, he's the best shooter. They're a horrible team. They want to make sure that they make at least 4 baskets. So they're going to keep giving the ball to Jim. So how many times should he shoot it to be 90% sure that at least 4 of them will go in? And so I put in the comment here. So if we want at least 4, that means we want 4 or 5 or 6 or 7 or 8, all the way up to a million, more than that. So we don't want 0 to 3. Now, when I type it into Google, I'm going to type it in just like this. It'll be 1 minus the binomial distribution. I did 1 minus because I'm counting up, so I have to figure out what I don't want. I don't want starting at 3 going down to 0. It's this question mark here that I need to guess. This question mark is how many shots Jim needs to take to be 90% sure that at least 4 go in. So for the quota problem, if we want at least 4, so I'm going to do minus because again, 4 or more is counting up. So I'm going to count down from 3. The binomial distribution, I'm going to start at 3. I need to plug in some number, which I'll do in a moment. There is a 50% chance, and I'm going to type in true because I want to add the 3, the 2, the 1, and the 0 together. And at this point, I now guess and check. So I want to plug in some number of shots that I think Jim needs to shoot to be 90% sure that at least 4 of them go in. So I'm going to try 6. If I try 6, so if Jim were to shoot the ball 6 times, there is a 34% chance that at least 4 of them will go in. So Jim needs to shoot the ball more. Maybe I try 10. Well, if you were to shoot it 10 times, there's an 82.3% chance that at least 4 of those 10 shots will go in. We need to have more shots because we want to be 90% sure. So if I do 15, well, if you're to shoot it 15 times, there's a 98% chance that at least 4 of them will go in. That's too high. So now I'm going to do something smaller, like let's say 12. That's 92.7. And if I do 11, that gives me to 88.6. So the answer to this problem is that Jim should shoot it, I would say, 12 times, at least 12 times to be 90% sure that at least 4 of the shots will go in, because 11 was just underneath, not 112, 12. So that's how the quota problems work, is you set up the framework of what's going on. It's almost always going to be the 1 minus and what you don't want. And then it's just guessing and checking to how many times you should do something before you get to your desired probability, in this case of at least 90%. So quick recap, mean is n times p. So the sample size times the probability of success. The standard deviation is the square root of the sample size times the probability of success times the probability of failure. And then the quota problems, you want to set up your framework for what you do or do not want. And then it's guessing and checking that second term in your command until you get the probability that fits the problem.